I'm Colin Robbins from Nexor. We're a company that specialises in secure information exchange. I'm going to provide a very brief background to a project called Capri that is an Innovate UK funded project, funded partly by industry as well. And the whole objective of the project is to run a cyber autonomous vehicle on public roads in the UK compliant with law. And so part of that is how do you take this vehicle, and that's a picture there of the Queen Elizabeth Olympic Park in London, which is where the trial will be run early in 2020. And so it's how do you run an autonomous vehicle on public roads legally. So it looks at a whole series of challenges. So some of those are to do with the vehicle side of things itself, such as the law requires you have windscreen wipers. Well, we don't have a windscreen, so somehow we've got to get around that kind of issue. But our particular role, both at Nexor and with Warwick, is to look at it from a cyber security perspective and how does that affect safety. So from a legal point of view, you have to present a safety case, and where you can't make the safety case, insurance picks up the residual risk. So really what we're doing is helping the insurance companies decide whether they can insure this thing before it goes on the road. And so if I look at the architecture, it's a very simple architecture. It's a fleet of vehicles that have a number of onboard systems. That's our Internet of Things, if you like. And it's connected to a back-end infrastructure, and that includes some gateway services. In this context, largely a fleet management system, which then down the bottom here has the fleet operators, and here the actual users of the system, which are the sort of the ride-hailing app. And so the premise is that the people down here have got complete control over the vehicle, etc. So one of the things that Warwick have done as background research is very much look at a reference architecture for a cyber autonomous vehicle. What are all the types of systems that make up a vehicle? How are they interconnected? And what are the attack surfaces? So a very sort of traditional approach to how you look at one of these sort of complex systems and do risk assessments around that based on methods of attack and attack trees. So within the Capri model is one of the areas where Warwick have then applied that model or subsets of that model, because obviously not all of it's relevant. In our particular fleet, it doesn't have infotainment systems. There's not a driver, so you don't need all the driver assist services. So it's really focusing down on the specific elements that this environment has, and then being able to do some detailed modelling of both the threat agents that are active in that environment, but also looking at the system critical elements that really needed to be able to do to build that safety case, particularly looking at things like the LiDARs and the radars and the ultrasonics, the eyes and the ears of the vehicle that's going to tell it where it is and whether it's safe to proceed. So from Nexor, we've done a very sort of similar piece of work, but we very much looked at the cloud side of that environment. So this is the fleet management system. And again, done a very traditional model. In this case, we used an automotive threat model that has been put out there in open sourced by the NCC. You used that threat model, applied it to the Capri environment, and then from those threats applied a stride-based risk model. So a very, very traditional approach. And have then gone back to all the suppliers of the various parts of that fleet management system and providing them the advice around the mitigations that they need to put in place. So it's a very traditional sort of cybersecurity side of things. But we then started to look at the overall risks of the system and said, well, actually, as an industry, our history of being able to secure one of these things is, okay, we put all this stuff in place, but actually our history shows we're not actually very good at it. So let's now just work on the theory of this is compromised. Now what can I do? Now, one of the interesting things about when this is compromised, it's going to communicate to the vehicle. And the vehicle has all the systems you'd expect to check the authenticity of the message and check the integrity of the message. But because it's this cloud system that's been involved, it will be a perfectly authentic message, and it will be perfectly intact, and it will be an integral message. it will just be not the end message the system intended the vehicle to receive. So how do we deal with those kind of situations? And that's where we've really started to focus the Nexor element of the research. And so within the Capri environment, what we've identified is, actually the communications you can send from the fleet management system to the vehicle are very simple. There are quite a few commands, but the two of real interest are, I can tell the vehicle its destination, right, where it's got to go to, and I can tell the vehicle to stop. So if I've got a fleet of 20 or 30 vehicles, and I've now got control of as a hacker of the fleet management system, I can start doing some really interesting stuff. For example, I can tell the vehicle to stop. So what happens if I tell that to stop right in the middle of a busy intersection? But more interestingly, what happens if I tell all 20 vehicles to go to that really busy intersection and then tell them all to stop? Have actually have the potential to cause major disruption. And each one of those individual vehicles will not know necessarily that there's anything wrong. So what we really started to research is, well, from a cyber security point of view, there's nothing wrong here. Someone's hacked the system, but we're now sending genuine messages. So how can we start to do that? And that's where we've taken a leaf out of safety engineering's book, where they use modeling and simulation to do this. So a heavy part of the Capri project is about modeling the safety of the vehicles, so presenting it with various scenarios. And Loughborough University have been really helping shape those scenarios based on some real-life accidents that have happened with the tram system in Nottingham, and modelling those back onto the sort of Capri environment. And so we've started to now feed in other scenarios into that modelling to say, well, let's see what happens when we tell all those vehicles to go to this particular place and stop, and see what happens. And at this stage, we're still working on that simulation to see whether the vehicles themselves actually have any capability to detect that situation. Because you would hope the vehicles have certain intelligence built in. If I tell a vehicle an instruction, go forwards now, and it sees a red traffic light in front of it, you would hope that the vehicle overrides that situation. So really starting to look to see whether the vehicles have got the ability to override that instruction to create that logjam and block the roadways. So that's very much what we're doing, and looking at it as a system as a whole. I'm now going to hand over to Carsten, who's going to sort of talk in a bit more detail about more of the advanced research side of things. Obviously, what I've talked about is the very traditional side of background stuff that we've done, and Carsten's now going to talk some more of the sort of research aspects of how we can look at that in more detail.
So, thank you. Yeah, so this is an Innovate UK project, and I don't know if many of you have done the collaborative research and development projects, but the idea is that up to about 30% of the project should be a research organisation like a university. So, as Colin said, cybersecurity is something that's quite important in modern connected and autonomous vehicles, and what we are looking at is developing new models, so new methods. So I'm going to talk you through a few of them now. I'm not going to go through directly and go through the slides, but basically what we're doing is we're applying some learning from a project which was funded in a previous round of Innovate UK, and that's a project called UK Site. It's about to end soon. It was from the very first major round of connected autonomous vehicles funding, and it involves a 41-mile connected corridor around Coventry. So within that project, what we did is we had a number of roadside units. So Coda is one of the big manufacturers of both roadside units and onboard units for them to communicate. And what we did is we did some risk assessment, and we developed a methodology, and we got some learning from that, and we decided you cannot penetration test everything in this massive ecosystem, and that's what Colin was saying about the reference architecture. We had to develop this reference architecture to give us a sight of how the complex ecosystem works. Yeah, so you can see here we've got GPS, LiDAR, radar, blind spot sensors, a number of different sensors, and they're combined so that data is fused into an analytical engine that then considers what kind of actions this autonomous vehicle should do. So this is a level 5, SAE level 5 autonomous vehicle. So actually there is a steward in the car, but no one driving, so it's a pod. And what we had to do is think, okay, well, what can we test? What parts can we test? So we do an approach which is to say, sometimes we'll do some analysis, other times we'll do simulation, and others will be actually the penetration, the physical testing. So there are some of the sensors that you can actually test physically. We do have at the University of Warwick in WMG a big drive-in simulator, a driver-in-the-loop driving simulator, which is a big Faraday cage. And we have got radar emulation.
Sorry, is it appropriate to ask a question?
Your chair.
Do you anticipate in the future those components like GPS, radar, LiDAR to be manufactured like Bosch will specialise in LiDAR and Lucas will specialise in the other components? So you, much like a modern car now, you buy those components and integrate rather than Ford making everything in-house?
So that's part of that complex system.
Yeah.
So there will be competition. So there will be, and a lot of OEMs, so for example, JLR does not have their own ADAS system, it buys it in. So I think you are going to see much more of services developed for that. Yeah.
They would be having a role in terms of...
Indeed, and that's why you need to see the whole architecture. And in fact, for us, Fusion developed some of its own. Fusion are part of the project, and they developed some of their own systems. So they developed their own systems and analytics. So you have all these systems that come in, but we can do some actual physical testing through emulation. Because we've got a big Faraday cage, we can generate signals. So we can spoof GNSS, so the navigation system. You can't do that outside because it will screw up everybody's sat nav, right? So there are certain things that we kind of can't do. So the first thing we do is decide which bits we're going to do in which kind of approach. What we then do, as Colin mentioned, is we use attack tree modelling, because what we think is there are many different threat modelling approaches. Previously, we've used composite modelling. So depending upon the kind of problem we look at, we'll use different approaches. So we used a stride-based approach here, but also some attack trees that we were developing. So what we're trying to do is look at, thinking about what are our types. So some of this standard stuff in threat modeling, who were the threat agents, what kind of goals, so attack-based threat modeling that we were doing, what's the attack surface, and you can see there the reference architecture that we used, and then the testing that we were going to do. But one thing I think that's important to recognize, and for those of you that came to the first keynote this morning, you'll have heard talk about dynamic rather than static. And this is really important for us because a lot of analyses that go out are very much valid at a certain point in time. And I think at least one person today mentioned an Innovate UK project, but I can tell you what it is. 5 stars, it's called. And that's about an MOT, a cyber MOT for vehicles, right? So it's Thatcham who work in it, and it came up in that first plenary session today. Well, that's a big challenge, because I can say something is secure today, but tomorrow there's new vulnerabilities that come out. Yeah. So what we do is, and I won't go into detail here, but some dynamic approach, and it's really about situational awareness that many of us know in cyber. So we've got beneath that a bit of modelling on, what happens if the vehicle changes or the environment changes? How does that change the threat landscape that we've got? So we're looking at this dynamic risk consideration that we're working on. We're also trying to bring together 2 areas that are important, and if any of you saw Peter Davies, who I do some work with, he's at Thales, and he looks after security for ASIN, we do some work together. He's a really good guy, and he talks about safety much more than cybersecurity. Yeah, so he says it's about being safe. Well, actually, that's what a lot of us are thinking of. So we've managed to get this, certainly in automotive, safety and cybersecurity They're very much interlinked. And that's important because safety is very well known in automotive, first off. But I'm trying to move on that conversation because I think we've won some of that argument. What I'm trying to say now is we need not just the safety and cybersecurity guys to talk together, but the verification and validation people. So what we are doing is looking at how we can actually consider, from the accidentology work and some other project that we've got where we're bringing these together, say, actually you can't verify everything formally, but what bits might we be able to formally verify, small parts of this very complex system? What other bits do we do informal verification? So in that sense, we might do some testing, for example. But what we're trying to do is say we need to map that with the threat modeling. We need to say, because sometimes verification will go, actually, it doesn't look too interesting there, so we're not going to do lots of verification. And this is a corner case, so this is important, so I'll do that. But if we can find where are the edge cases in terms of where an attacker might want to orchestrate your bad luck, where he might want to put you in a position, then we can say to the verification guys, are we confident enough that we've verified in this area? So that's a new approach that we're doing that we're sort of calling security-informed verification, which really ties together the two parts. And they're the key innovations that we're trying to push forward for this project. And it's pushing forward these ideas, these new ideas that we're hoping to help ensure that we've got confidence when we put these trials out. So these trials will be running around the Queen Elizabeth Olympic Park in just over a year, so not very, very long. And we're trying to do holistic mixed mode approaches, while Colin's looking very much at the cloud base. We're working together to make sure there are no gaps, but we're looking at the vehicle and edge kind of environment.